Welcome back. We're almost finished with lecture 8. Okay, we have couple more concepts to look at. One is the idea of a piecewise defined function. And a piecewise defined function simply is what its name says. Notice that the domain is split into pieces. Now, this is not something that we're unfamiliar with. We've been looking at that in terms of absolute value. Remember, the absolute value of x is x if x is less than 0. I'm sorry, is minus x if x is less than 0, and x if x is greater than or equal to 0. That's exactly what we've done. We've split the domain into pieces. And we do the same thing here. So f of x is defined to be one thing if x is less than or equal to 0, and another if x is greater than 0. Is that a function? Yes, because for a given x, I have exactly one way to find f of x. Okay, let's look at some examples. F of -1. First of all, I have to figure out what piece of the function I'm using. And I'm going to call this piece 1, where x is less than or equal to 0, and this piece 2, where x is greater than 0. Okay? So this is piece 2 of the domain. This is piece 1 of the domain. Now, for f of -1, I know that -1 is less than 0, so I'm using piece 1. Okay? Because where -1 lies in the domain is right here. And so f of -1 is defined to be f of 2 times -1 plus 1. It is using part 1 of our domain, and so that's the way the function's defined. I replace x with -1, and I get my one and only, my unique y value. It is a function. Okay, what's f of 0? Where does it fit? Well, 0 is equal to 0. So it's less than or equal to 0, so I'm still using part 1. 0 fits into this piece of the domain. So f of 0 is 2 times 0 plus 1, which is 1. Okay? For our third example, what's f of 2? Well, 2 is greater than 0. So this time I'm using the second part, or the second piece of my domain. And so f of 2 is defined according to the second definition of f. So it's 2 squared minus 1, which is equal to 3. And so what do I have for the function value 3? Notice it's a function, perfectly well defined. If I know where my domain, my argument lies in the domain, I know exactly how to find the function. Okay, one last concept, and this is not new, but we're giving it in terms of the function now. The domain of a function y equals f of x is the set of all real numbers x for which the expression's defined. Remember, the domain is associated with the x value, and that is what we call the independent variable, because I choose x first. From that, I then figure out what y is. The range is the set of y values, which is what we call the dependent variable. Just think of the terminology. We say y is a function of x. Y depends on what x is. Okay, so when I'm looking for domain, I have to figure out any restrictions on what x can be. And notice that we have two expressions in this function. We have two parts. One is square root of x minus 1 is one expression, and the other, if I think of this as a fraction, we have 1 over x squared minus 4. And each of those have unique restrictions. Okay? Here, I know that x minus 1, it's under the radical, so it has to be at least 0. So I know x has to be greater than or equal to 1. And at the same time, it's got to satisfy both. The denominator cannot equal 0, okay, because it's in the bottom of a fraction. So x squared cannot equal 4, so x cannot equal plus or minus 2. Okay, so what does our domain of the function look like? Think of a number line. Okay, first of all, x has to be greater than or equal to 1. Okay, so that's the first restriction. We're only in this portion of the number line. And x can't be negative 2, so there's got to be a hole there. Well, negative 2 is not in the domain anyway, so we don't have to worry about it. But x also can't be positive 2. So we have to put a hole right there. So what's the domain? It's this portion and this portion. So the domain in interval notation, remember it does include 1. 1 is in the domain of this function. 1 in the 0 in the numerator is fine. But we can't have 2 because 2 would make the denominator equal to 0. And so we have the domain of our function. Okay? One last example, and that is an application. Okay? When you move on, the whole idea of functions is to let us be able to represent scenarios, represent situations, and then work with them. So here's a scenario that you will run into in a calculus problem later on. And you may think back to kindergarten. You probably built yourself a little pencil box. You may have done this out of a piece of cardboard. And this is exactly how it works. So let's assume we have a piece of cardboard that's square, 36 inches by 36 inches on either side. So you take a corner and you cut out an equal square from each side of this. And then you fold along the red lines. You fold it up and you get yourself a box. Now, what are the dimensions of that box? What's the height of the box? Well, when you fold it up, you're going to have a dimension of x. Okay, do you see that? When you fold it up, it's going to be this distance will be folded up. That's going to be your x. Okay, right here when you fold it. Okay, then remember, the top will be open. So you'll have your box. Now the base is going to be a square. Okay, because we initially had a square piece of cardboard. And we fold it up, so what does this length become? This length right here, actually this, will become your width, and this would become your length. And what is that? Well, remember the whole distance is 36, but we're subtracting x from each end. Same thing here. So what we're left with is a dimension of 36 minus x and x, 36 minus 2x. And it's the same way in this direction. 36 is the total length minus an x here and an x here. So our dimensions are 36 minus 2x and 36 minus 2x. Okay? And it says express volume as a function of that length x. Well, we can do that easily because we know volume of a box is length times width times height. Okay? And what's the length? It's this distance, 36 minus 2x. And the width, because we started with a square and we cut out equal pieces from each end, it's also 36 minus 2x. And the height is what happens when you fold it up and you get x. And what would the units be? Well, each one is an inch, so it's cubic inches. 36 minus 2x inches by 36 minus 2x inches by x inches. So it's that. If I want to simplify that, I can write as x times 36 minus 2x squared cubic inches. All right, I'll write it out. Okay, now the next question is, what's the domain? Well, are there any restrictions on this equation? Certainly not. But we know that we're talking about volume. And volume only makes sense if these dimensions are positive. So we know that x has to be positive. Otherwise, it doesn't make sense. Technically, we could say x is 0, but let's just assume that x is greater than 0, so that there's something to fold up. We also know that these dimensions have to be positive. All right? So that means negative 2x has to be greater than negative 36, and if I divide by negative 2, I get that x is, remember, reverses the inequality, x is less than 18. So both of these have to happen at once. So I know that x is greater than 0 and less than 18, or I could express that in interval notation, 0 to 18. That is the end of Lecture 8. Thank you.